Now it's time for a theory lesson on thermistors. Shown here in this graph is the resistance versus temperature curve for a typical NTC thermistor. The base resistance is 10,000 ohms at 25 degrees C, and the resistance drops by a stunning 4 orders of magnitude when the temperature increases by only 100 degrees C. The Steinhart-Hart equation models the highly nonlinear behavior of thermistors. These guys were geophysicists who published their research findings for thermistors back in 1968. And when you're the first guys to publish an equation or a physical constant, they usually get named after you. The logarithmic terms in the equation and the inverse relation of the terms to temperature do two things. They explain the large fall-off in resistance over a narrow temperature range, and they make for a very smooth-shaped curve. Note that the temperature must be calculated in degrees Kelvin, and there are 3 proportionality constants to keep track of. Yuck! I like this form of the Steinhart-Hart equation much better, if you can like equations, that is. First, you make the substitutions for constants B0, B1, and B3 as shown here in the slide. Then you are left with an equation for temperature that depends on any 2 points, R and T, and only one material constant, beta. The equation is easier to program in firmware. You measure the resistance of the thermistor, and then you solve for temperature. I found this thermistor online in the form of a through-hole resistor. Actually, it looks more like a matchstick than anything else, but you get the idea. It has the typical accuracy of 0.1 degrees C to 0.2 degrees C, seems a bit slow at 10-second response time in air, and has modest power dissipation of only 30 milliwatts. My application is around room temperature, so I picked the 10,000 ohm base resistance. Beta is 3,890 degrees K, and there's one other nicety on the website. I can download the data for resistance versus temperature. And the data is in the form of an Excel spreadsheet. Now that's pretty slick. I can use the data to implement a table lookup routine in firmware. No need to do any calculations of a logarithmic form. I still need a way to measure the resistance of the thermistor, however. This simple voltage divider circuit can do that. However, it won't be accurate unless the voltage source and the fixed resistor are also accurate. Alternatively, you could measure V with the same analog to digital converter used to measure the thermistor voltage. And you could buy a precision fixed resistor and use that as a reference. It's best at first to calculate the accuracy you really need and at what cost. Let's look at the accuracy of the voltage source. The standard PSOC reference voltage source has an accuracy of 0.5%. You could use a precision shunt reference from Texas Instruments that has 0.2% accuracy. However, that will add 96 cents to the production cost of your system. You'll save money if you come up with the circuit diagram shown here and purchase a precision resistor for only 5 cents. The VDAC in your PSOC kit provides a fixed voltage that can be turned on and off at will. The op-amp provides extra current drive capability that the VDAC does not. The data sheet says the output resistance can be as high as 16,000 ohms. Unfortunately, the VDAC voltage accuracy is poor. The data sheet says it's a gain error that can be as high as 5%. So to reduce that error, we employ a 0.25% accurate 10K ohm resistor from Stackpole Electronics that costs just 5 cents. Then we measure the current across the resistor, and the accuracy of the measurement depends mostly on the resistor accuracy. So, what about firmware for your embedded system? You need to write code to set up the ADC. You have to sequence the inputs and calculate actual current and temperature. The equations for temperature are highly nonlinear, logarithmic, as we have discussed. So that could tax the processor. You can use table lookup methods if you can download an Excel table from the website of the thermistor manufacturer. And if you do this, make sure you have enough onboard memory to store all the data. Let's recap. We discussed the core technology and calibration equations that govern thermistor. Now let's discuss the accuracy, range, and typical applications for RTDs in the next video.